Welcome back to our series on multivariable calculus. In this episode, we're not going to cover a new lesson. Instead, we're going to explore the justification behind the magnitude for the cross product. So this will be a supplement to the prior video on the cross product. Okay, here I have it laid out. We've got the definition of the cross product as well as what we're targeting. We want to try and prove that the magnitude of the cross product is indeed the magnitude of A times the magnitude of B times the sine of the angle between them. In order to do that, we have to first begin with the magnitude based on the definition of the cross product. So in order to simplify most of the derivation, I'm actually going to calculate the magnitude squared because that will remove the square roots from the remainder. We'll go ahead and take the square root at the very end. Okay, well, I need to square each one of these three terms because the magnitude of the cross product will be the distance formula or the Hyperpythagorean theorem applied to the components of the cross product itself. So applying the cross product magnitude here, it's going to be A2B3 minus A3B2 quantity squared plus, because I'll square away that negative, A1B3 minus A3B1 also squared plus A1B2 minus A2B1 quantity squared. Okay, and then we have to expand out all these terms, and I'm going to do it on 3 lines, one line for each one of these. So the top line is going to be A2 squared B3 squared minus 2A2 A3 B2 B3 plus A3 squared B2 squared. The middle term is going to produce plus A1 squared B3 squared minus 2 A1 A3 B1 B3 plus A3 squared B1 squared. And finally, the last one's going to produce A1 squared B2 squared minus 2 times A1 A2 B1 B2 plus A2 squared B1 squared. Okay, now I'm going to do something unusual. I'm going to add and subtract something from each one of the terms. That will make the factoring that we're about to do a whole lot easier. So what I'm going to do is add A1 squared B1 squared and subtract it. A1 squared B1 squared. And I'll do the same thing to the next 2 lines. A2 squared B2 squared minus A2 squared B2 squared. And finally, plus A3 squared B3 squared minus A3 squared B3 squared. Okay, so far we have set up all the algebra we need in order to pull out what our answer is. I'm just going to reorganize things a little bit. So let's begin here. I'm going to write, the next line's going to be A1 squared B1 squared plus A1 squared B2 squared plus A1 squared B3 squared. And you can take a look at that to see the common factor, plus A2 squared B1 squared plus A2 squared B2 squared plus A2 squared B3 squared. And again, you can take a look at that for its common factor, plus A3 squared B1 squared plus A3 squared B2 squared plus A3 squared B3 squared. And you'll see that this one also has a common factor, okay? What remains are these negatives here and all the cross terms. So I'm going to write them down as one long negative. So it'll be minus A1 squared B1 squared minus A2 squared B2 squared minus A3 squared B3 squared. And then minus all these cross terms. Minus 2 A1 A2 B1 B2 minus 2 A1 A3 B1 B3 and minus 2 what's left over? I've got the 1s and 3s and the 1s and 2s of the 2s and 3s, A2, A3, B2, and B3. And that's it. We've taken all of these terms and we've configured them so that we can factor it, okay? Well, if you look carefully, A1 factors out of here, A2 factors out of here, A3 factors out of here, and what's left is B1 plus B2 plus B3 squared. So those first two, the top 9 terms are all A1 squared plus A2 squared plus A3 squared times B1 squared plus B2 squared plus B3 squared. And then all of this remaining stuff, that's equal to minus A1 B1 plus A2 B2 plus A3 B3, and it's the whole thing squared. That's what produces these 6 terms right here, and it's negative. Okay, if we look really closely, we can see that this is actually the square of the magnitude of vector A. So this is the magnitude of vector A squared. This whole thing right here, that's the magnitude of vector B squared. So that's magnitude of vector B squared. And then finally, this guy right here is actually the dot product of vector A and B. And if you recall, one of the ways to calculate the dot product was the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. And of course, the whole thing is squared. So this would be minus the magnitude of vector A squared, magnitude of vector B squared, times the cosine of the angle between them. So that there is representative of the fact that this is the dot product and it's squared and it's got a minus in front of it. So there's the dot product, AB cosine squared theta, and it's all squared. Okay, we can apply a factorization and a trig identity at this point. We can pull out magnitude of A squared and magnitude of B squared. And what's left is 1 minus cosine squared theta. Of course, 1 minus cosine squared is sine squared. So this becomes magnitude of A squared, magnitude of B squared, times the sine squared of theta. And remember, all of that began as the square of the magnitude of the cross product. So now we have our answer. The cross product's magnitude is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. And there's the proof or derivation of why the magnitude of the cross product depends upon the sine, whereas the magnitude of the dot product, of course, depended on the cosine.